Hi, my name is Ari Everett. This is Conversation Piece 1 in the theory module for my 4-bit binary to gray code converter. This is for CSC120, Intro to Digital Design, for Professor Cody Anderson in the fall of 2023. Here's my webpage I built and submitted to Canvas with the goal, design process, implementation, reflection, and some videos and pictures. I'll do a quick overview of this and then get to the demo. So my goal was to deepen and extend my knowledge beyond the Module 1 lessons, create a successful conversation piece 1, as well as create my final product from beginning to scratch to completion, which was the 4-bit binary to gray code and converter. So my initial design process was I looked at other people's projects to see what I was getting into. I felt a little bit behind because I'm taking CSC110 concurrently, and some others' coding skills are a bit beyond mine. I took a look at some topics we came up in class, and as well as in the video lessons. I looked at 15s and 9s complement, which I thought was cool, and the method to do this was straightforward in taking the very highest bit or the highest possible number in that system and subtract it from whatever you're trying to convert it to get the complement. When I got into the code, it was a bit beyond me. Strings, arrays, switching methods, like others have used, were beyond my capabilities for now. Unicode, I found that Java actually has an embedded library standard for Unicode conversion, so that didn't seem too interesting to me. I'm sure I could create my own in the future. But I landed on gray code converter. I thought when this was brought up, it really piqued my interest because if I were to create a binary coding system myself, I thought it would be something and look something like this. I thought the efficiency and the unit distance and making it faster for switching operations was really cool. I remember from a video we watched in our first module where explaining in computer science, someone who created a new language like Beltran or another assembly language said they're a lazy programmer, and so they came up with this faster method. So it speaks to their ingenious and genius at the same time. Quick background on design process. So I dove into that topic. I looked at the history and the methods of it. It was created by Frank Gray in the 1940s in order to reduce errors and have faster switching operations. I created a high-level conceptual circuit here. You can see in the middle picture, where I basically wanted to have in my logic circuit 4-digit input to a 4-digit output and the conversion somewhere in between. I studied about the different logics and methods to convert from binary to gray code, which is the reflective or mirror method and the XOR method. I created and mocked up the truth table and then a logic circuit with gates, and then I have the TTL circuit as well. At the very end, I had an epiphany and said, I can do this in Java. It's very rudimentary and there's no computational logic in it, but I can still create something with the knowledge that I have. It would be good practice to help extend my abilities. So implementation goes here. Here's my video, a picture of Logisim, and the code from NetBeans, which is my IDE for Java, and then my reflection at the bottom. Let's hop into the demos here. So here is the logic circuits that I've made, one with just gates and for a conceptual circuit, and the other one with the built-out TTL ICs. So at the top here, the method that I found was that you can XOR the following digits except for the most significant bit. And I'll move over here to this portion of the write-up, which is there is the reflective method, which is similar but opposite to the binary switching method, and then the XOR method. The reflexive method was really cool, actually. So when you fill out all possibilities on a binary chart, let's say BCD 4-digit, you start from the least significant bit and go 0, 1, 0, 1, 0, 1. And then one position up, you go 0, 0, 1, 1, 0, 0, 1, 1. And then one position up, 4 zeros, 4 ones, one position up, you do the next power of 2 there, and so on. In gray code, you do a mirror for every 2, the 4, and then 8 powers of 2 method here. So I explain it here in the 3-bit example. You go 0, 1 on the least significant bit, and then there's a mirror after that 1, 0, based on the principles of just switching 1 at a time. And then the next 4 is a mirror of the previous 4, and so on. You can create your 3-bit example and your 4-bit example here. I chose the XOR method, which is listed here. Let's say we have binary 1, 0, 0, 1, and we want to switch this to gray code. You drop the most significant bit, and then you XOR the remaining in the binary, and that will give us the remaining digits in the gray code. So 1 and 0 XORed is 1, 0 and 0 XORed is 0, and 0 and 1 XORed is 1. You can think of the truth table, it's 0, 1, 1, 0, or if you have opposite or just an odd number of ones in your expression, that is when you get a 1. And then we have the same 1, 0 or 1s, you have a 0. I created, using that method, I created this logic table here, and then using this method here, I created the logic circuit. I had kind of peeked ahead. I saw that there are things called K-maps and Carnot maps, which maybe would help me come up with this faster, come up with a Boolean equation to simplify this and create this. But through process of like trial and error, this is what I created here. So A being the most significant and W being the most significant on the gray side, A binary side, it's a straight pass through. Then A and B, you XOR those together and get X. This is an iteration, and I had to improve this in Logisim here. I created the branch after the XOR, which the error is it considers A and B XOR together. It just needs to consider B. So I need to switch this branch to B. I'll show you that in the schematic here soon. B and C together and C and D together. It gets us our W, X, Y, Z. So let's hop into here. I've mapped that out here successfully. Let's take in a poke. I've put in 0, 0, 1, 1. And so A goes straight through to 0 here. And then A branches off and goes to this XOR. B goes straight to this XOR. And when it branches off, it doesn't go after the XOR. It goes before. In my schematic, I initially had it going like this, which created an incorrect output. And so on. And so 0, 0, 1, 1 equals the output 0, 0, 1, 0, which we can go A pass through 0. We double check our math and method here. 0 and 0 is 0. And then B and C together, 0 and 1 is 1 XORed. And then C and D, 1 and 1 XORed is 0. So using that, I built out the bigger schematic. I used the 7486, which was a chip that we did not have available to us, but kind of came to knowledge in the last lab for carport, where we used an OR and a NOT gate to emulate an XOR gate. We could simplify down to this. So I thought this was a really great time to use this chip here because this is all just XOR gates. So we create our 4 input binary 4-bit inputs, and the output is the grade code 4-bit output. Here down here, we have our power and power cord and our ground wire to make sure the electrons are flowing through properly. I've also input 0011, and you can see here 0010. We can even change that to 0010, and the gray code output is 0011. And we can double check that math because C and D XORed is going to be 1, which is at least significant bit here. You can follow the wire diagram and how they branch off into A, most significant bit. Binary goes to straight to most significant bit gray code. And then down here, it goes into our very first XOR gate combination in the channels here. I had to look up the chip schematic, and it's a counterclockwise rotation here of the 1, 2, 3, 4, 5, 6 different input channels here. So that's why I chose to go in this roundabout way. B here, you can see how it branches off and goes to the second bit, or the second position after the most significant bit, along with the C here, and then so on with C and D. Now I'll hop over to my NetBeans Java IDE, and I'll show you the workings of this. So there's no computational code here. It's all, I guess you could say, hard-coded or hardwired in here, but we just learned about if statements. So I had to look up some different if-else statements and the operators to describe how the integer or double would equal the hard-coded binary 4-bit digit, and then output. So just to run the program here, and what we want to do is input 4-bit binary digit, right, and get the 4-bit gray code output. So I hit run here at the top. It says, welcome to the 4-bit binary to gray code converter. Enter your 4-bit binary number. I will do, let's go 0110. Enter. Your binary number in gray code is 0101. And we could double check that here. Most significant bit stays the same. The next digit here in gray code is 0 and 1 XORed, which is 1. The next position is 1 and 1 XORed, which is 0. And the next position, 1 and 0, is 1. So that is correct. Let's run it one more time just for fun. What is 1111? The highest we can get, 15 deci, here converted. Your binary number in gray code is 1000, which brings up another great property of gray code with this, which is the cyclical nature property of it, in that it will only be one bit change, one switch change to 1 to 0 to go back to the very beginning of the cycle. And then it's, again, cyclical in nature where it all resets to back one. It's just one switching. So that is my Java program, and that is my logic schematic. Some reflections on this. I think that I mentioned that maybe there are some more chips or schematics where I can simplify this even further. I know it's just one chip, but maybe even an IC board, we don't need as many wires, as many inputs and outputs. Maybe there's like something that combines something. So it was really cool when I searched in here in Logisim for the 7486. There's all sorts of other chips I didn't know existed. So we can maybe further simplify there to make it a more efficient process. I mentioned before the iteration that I had to do here because I had the branch off going after the XOR. So that was really nice to see in modeled out because I was able to catch my mistake and visually see it. And then on the NetBeans side, I think the expansion here could be, I could like, instead of hard code it, I would input some computational logic within the code. I don't know how I would do that without maybe switching strings and arrays and parsing information. But I was thinking in my head, maybe I could use the modulo to help do some, like a modulo over and over again in each digit for each 4 digits to come up with some sort of conversion. But that's it. Thank you very much.